Hello and welcome to Lesson 7.2 on writing rational functions in general form. So what this lesson is about is analyzing general form rational functions. When I say general form, a typical rational function is written as a ratio of polynomials. We kind of talked about that definition last time, saying p of x is a polynomial divided by q of x, right? So this ratio we call a rational function, okay? So anyway, what we're looking at is the features of rational functions written in that form. So we're looking for x-intercepts, y-intercepts, horizontal asymptotes, vertical asymptotes, and then a new feature that maybe you haven't heard about before called removable discontinuities, which we also call holes. So we're going to see what those look like, how to find them, and stuff like that. Now, I must preface that this lesson comes from a very exploratory point of view. This works much better in class as a group exploration as opposed to an individual learning lesson. You might be able to find these rules online elsewhere, or maybe even a past video of mine. But I'm going to try and balance between doing the exploration with you, but also just for the sake of time, just kind of showing you what the rules are. Because really, the power of this lesson kind of comes in you doing it, your own actions and observations. That's really where you develop the deep understanding of why we have these rules and blah, blah, blah. So I encourage you to pause the video, start trying these for yourself like you would in class if this is your first time watching the lesson. If not, at the end of the lesson, I'm going to go through all of what the rules are, all of the sort of summary of what you need to know, and work 2 example problems on how to use those rules. So really, if you just want to see what the rules are, and you just want to see how they're used to graph rational functions and analyze them, go all the way towards the end of the video. You should see, let's see here, this slide. So once you see me working through this, here's all the rules, and then there's 2 example problems here. That's at the very end of the video, though. For the first part, I'm going to kind of go through this explaining the why, the reason behind why we have rules and blah, blah, blah. So the first thing we're going to do is look at vertical asymptotes. Now, a vertical asymptote, remember a line that, scratch that. An asymptote is a line such that the distance between your function and that line decreases to 0. Yeah, it's continually decreasing and going to 0. So like if I have a line like this, and then I have a curve like this, the distance between that curve and this line is decreasing. That is the mathematical definition of asymptote, okay? A vertical asymptote means, so I've got some line that's vertically positioned. And a function, well, if it's approaching an asymptote that's vertical, it can either go up and approach it like this way, or it can go down and approach it this way. But it really can't do anything else. It either has to go up towards positive infinity or down towards negative infinity. So to figure out how you find the vertical asymptote of a rational function in general form, which is, again, p of x over q of x, it is suggested that you do the following. So you pause the video and do this on your own. It says completely factor the polynomials in the numerator and denominator, so both top and bottom, and then graph it using technology. So something like Desmos or, whatever. Putting on Do Not Disturb just in case I get any notifications. Just graph using technology, and then using that, look at where the vertical asymptotes are. So I'll do like the first one, but I'm not going to do all 4 because the video would be really long. It's already going to be like probably an hour. I don't know. But let's just do a few. Yeah. So number 1 here, in factored form, I've got x minus 3 over 5x plus 10. If I factor that, the numerator I get x minus 3, and the denominator I have a GCF of 5, and that factors as 5 times x plus 2. Okay? And so what I'll do is I'll go to Desmos and I'll just kind of graph this and I'll look at where the vertical asymptote is. So x minus 3 over 5 times x plus 2. So I'm going to go over here, delete whatever I was doing here. Oh, I guess that was from the last video. So I have, what was it? What did we say? X minus 3 over 5 times x plus 2. Okay. And so I see, just based off this image, right, I could kind of see this graph going up, 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 up. And what's it getting close to? Well, it's getting close to -2, it seems, right? I wish I could kind of do an overlay on top of Desmos. I don't really know how to do that, so I'm sorry. But I'll type it. If you see x is -2, you can really see how that we're getting closer and closer to that vertical asymptote, right? And that's it. So I will come back over here. I'll say x is -2. And at this point, so if you get the gist, pause the video and try 2, 4, and 3. 2, 3, 4. Yeah. So I'll try that. I'm going to go ahead and do 2, but then I'll just brush through the answers of 3 and 4. So on number 2, if I factor the numerator, it stays 2x. I should probably do that on factored form down here. 2x, and on the denominator, that's a difference of squares, x squared minus 4, which we factor as x plus 2, x minus 2. Okay? So let's go graph this. 2x over x plus 2, x minus 2. So I've got 2x in parentheses, x plus 2, x minus 2. Okay, so I've got this interesting shape that does not quite look like the parent function, right? Maybe the right and left branch do, but something's going on in the middle there that's happening. So I can see that this appears to have 2 vertical asymptotes, seemingly at 2 and -2. Again, I can type that. Here's 2, and here's -2. So, I can make both of these red, probably. Can I make it red? Oh, here we go. Red and dotted. I'll make this red and dotted. So you can kind of see those asymptotes right there. And so I just write this down, right? That's where it's getting closer and closer to both 2 and -2. Okay. Now, for sake of time, I'm just going to go ahead and factor the other 2 and tell you what the vertical asymptotes are. You can graph them in Desmos and see it. For number 3, I can take a GCF of 3 out over. Let's factor this. So 2x squared minus 7x minus 4. Let's see. Let's put a 2x here. Let's put an x here. 2 times 4, so -4. That gets you -7. Well, it gives you -8, but then you add 1 x to it, you get -7. So there it is, fully factored. My vertical asymptotes, if you graph this, are going to end up being x equals -1/2 and x equals 4. So those will be your vertical asymptotes. Again, you can type that in Desmos and see that, okay? I'm going to repeat this for number 4. We've got a factored form that looks like 6 and 3 on top, x plus 6 times x plus 3. And on bottom, that looks like a perfect square trinomial. That's x minus 5 squared. Okay. And I will find that my vertical asymptotes, I will only have one at 5. Okay. So we put all this together. You've made the observations, and what the connection you're trying to make is by looking at factored form and the vertical asymptote, right? And I say, well, let me look at the numerator, denominator, and so forth. And what's special about the asymptotes in connection to this factored form? And hopefully you're seeing it. You don't need me to say it, but if you don't see it, the bottom denominator, right, the thing in the bottom, that is determining where your asymptotes are. -2 is a root of the denominator here. 2 and -2, they're roots of the bottom polynomial, which is factored as x plus 2, x minus 2. So the idea is whatever makes the denominator 0, see like right here, it's 2x plus 1. I found that x is -1/2. That's 2 times -1/2 plus 1, which is negative 1 plus 1, which is 0. If you make the denominator 0, you're having some constant divided by 0, right? And division by 0 is undefined. And so because of this undefined nature, when I get close to that 0, it's going to either reach upwards towards positive infinity or reach downwards towards negative infinity, but I can't hit that number that makes the denominator 0. And so that is the vertical asymptote. So the rule here, the takeaway is the roots, or you could call them zeros, the zeros of q of x are the vertical asymptotes. Yeah, that is essentially the idea. You could also say, another way to write this is to find the vertical asymptote, and if you could skip forward, but to find the vertical asymptotes, you can set the denominator, the bottom, equal to 0 and solve for x. And that's your rule. Okay? So for any general function, p of x over q of x, if you find the roots of the denominator, if you find what makes the denominator 0, you're going to find vertical asymptotes. That's it. Okay, so we move on. We go to the next one. We start talking about horizontal asymptotes. So it says, for each of the following, you're not going to factor on this. There was a connection between roots and vertical asymptotes. That's why we factored, okay? Here, it has to do with the powers of your polynomial. In particular, the highest power, which remember we call the degree. So what you want to pay attention to is the degree of the numerator and the degree of the denominator, okay? Once you sort of make a note about the degrees, graph it using technology and see where the horizontal asymptote is, okay? So you'll have a line like this, and the function will be getting close to it, right? So that's what you're looking for, is where does the curve kind of flatten out horizontally, okay? Now, I'm going to do a few of these, but again, it's suggested that you sort of pause the video and do all 9 for yourself, okay? So let's try this out. For number 1, I'm just going to analyze the degrees. So for the degree, on top, it's the highest exponent. It's 4x to the 1, so the degree is 1 on top. Over, on bottom, the degree is 1 also. Okay, so the same degree, right? 1 over 1. What is the horizontal asymptote? Well, let's graph this. I've got 4x minus 3 over 4x plus 7. So I've got 4x minus 3 over 4x plus 7. Okay. So I'm going to have to manipulate this around. Let's see here. So it starts to get flat over here. Say, what y value is that? So you can see it's getting flat on both sides. I'll zoom in up here, and it looks like it's getting pretty close, if you can tell, to 1, right? Each of these squares is 1. Notice if I type y equals 1, you can see that closeness, right? You can see it at y equals 1, we're approaching that asymptote, yeah? So I'll come over here, and I'll write y equals 1. And then I'll do the next one, 6x squared minus x plus 7 over 3x squared minus 4. Oh my gosh, that's a lot. What was it even? 6x squared minus... What was it? X plus 7 minus x plus 7. And I don't even remember what the denominator is. 3x squared minus 4. Okay. 3x squared minus 4. Okay. So I'll notice that there is still this sort of flattening, right? It's kind of a weird looking curve, but it seems to be flattening here at 2. So if I say y is 2, Yeah, that makes sense. It looks like it's sort of flattening out at y equals 2. So I'll make that observation. Okay? So y is 2. By the way, I should be paying attention to the degrees, right? For the degree, make a better D here. For the degree, I had a degree of 2 on top and a degree of 2 on bottom. Okay? And then y was 2. Interesting. Now, I'm not going to do the next one, but if you plot this in Desmos, first note the degrees. The top degree is 3. The bottom degree is also 3. And the horizontal asymptote is going to be y equals 3 over 2. Or you might say y is 1.5. Trust me, if you graph this in Desmos, that's what you see. So, that's it. There it is. Are you seeing a pattern yet? Maybe, maybe not. Yeah. If you do see the pattern, you can kind of write it down. So we kind of move on. Let's do 4 and 5 and 6. So let's first notate the degree. For number 4, the degree on top is 1, and on bottom, the degree is 2. So remember, it's just the highest exponents. X to the 1, that's x squared. That's where I'm getting that. If I graph this, what is the horizontal asymptote? Well, this is just a slight alteration on number 1, where we made 4x squared on bottom. And so I have this curve. So notice this blue curve, right? Well, it seems to have an x-intercept there at 3/4, but it does flatten out, right? It's flattening, and it seems to be flattening at 0. It's going towards that x-axis, right? If I say y is 0, that seems where it's getting flat. You will notice something here. Even though this is an asymptote, horizontal asymptote, we're crossing it, right? We're actually going over the asymptote. And so this is a good opportunity that maybe your Algebra 1 teacher said an asymptote is a line you get close to and don't touch. That's not true. That's not true at all. You can touch it, yeah? You can see it right there. The asymptote is described by the distance between that line decreasing down to 0, which it is. It's going to 0. But that doesn't mean they don't touch. It touches right there. So all this, I'm going to say y is 0. Let me erase this. Okay. Do the next one. I'm just going to make another slight alteration. So I make that one go. And now I'm changing this one to not 3x squared, but 3x to the 4th. And I'll notice again, so it's a similar shape as that last one, number 2, but it's still flattening out here at 0. Last time it was 2, now it's moved down to 0. And it doesn't matter that I have this curve down here. Who cares about that? The horizontal asymptote is about the behavior on the left and the right. Yeah. So it's also at 0. And if, darn it, I forgot to talk about the degree. What was the degree? Because this is important. We're making a connection between these two. Well, the degree on top is 2, and the degree on bottom is 4. And I'll do this now for number 6. The degree on top is the highest exponent, 3, and the degree on bottom is the highest exponent, 4. And I see that the horizontal asymptote, if you type this, I'm not going to, you'll find that just like the previous 2 examples, it is 0. Interesting. So I'm not sure I quite saw a pattern with these, but I definitely see a pattern here because they're all 0. And I kind of noticed that between the degrees, here, and here, they're all bigger on bottom, right? The degree of the denominator is higher than the numerator. That's sort of the pattern here. And every time that has been happening, I'm getting y is 0. So maybe we'll come back to that idea, yeah? Lastly, we're going to look at 7 and 8, and then also 9. I'm going to make another slight alteration. And on this one, it's 4x to the 1, but we do 4x squared on top. And so I get this weird-looking rational, right? Does this have a horizontal asymptote? I mean, you could take this horizontal line. Does it seem to be flattening out anywhere? I mean, does it, no matter what I pick for y, I mean, this doesn't get flat horizontally. So, conclusion, there's none. There was no horizontal asymptote. And the degree on this one was 2 over 1, right? The degree was higher on top than on bottom. If I go to number 8, I'm going to see that same idea of the degree on top is 3, the degree on bottom is 2, so it's higher on top than on bottom. And let's type this in. So it's cubic on top and squared on bottom. So let's change this to cubic on top and squared on bottom. Well, shoot. Another interesting curve here, but one that also doesn't seem to have a horizontal asymptote. It doesn't seem to flatten out horizontally anywhere. It's never approaching a constant value. So we'll see here that the trend is we don't have one. In fact, if you graph number 9, again, you're going to see that the degree on top is 5, on bottom is 3. It's more on top and on bottom. And if you graph this, you will not see a horizontal asymptote. And so there it is. 9 examples to kind of establish what are the rules here. Maybe I am seeing patterns, right? I certainly see 2 patterns pretty clearly. The contrast between it being more on top or more on bottom, right? So on here, here, and here is more on bottom. It was all 0. So if I try to formalize these rules, if the degree of p of x is that's the top, right, is less than the degree of q of x. So these are the examples 4, 5, and 6. The degree of the top is less than the bottom. I saw that the horizontal asymptote was y equals 0. This just seemed to be true based off those examples I was doing. If I did the vice versa, if I made the top bigger, so I said the degree of p of x, which is the numerator, is greater than the denominator, well, then I had no horizontal asymptote, right? That was the examples 7, 8, and 9, where the degree on top is all more, but they have no horizontal asymptotes. Now, what was this last one, the number 1? So here, you notice that the degrees are all the same, 2 to 2, 1 to 1, 3 to 3, right? But what's the connection between this degree and then these? Well, what you want to pay attention to is the leading coefficients. 4x over 4x. 4 divided by 4 is 1. 6 divided by 3 is 2. And 3 divided by 2 is, well, 3/2, or 1.5. So, what appears to be the rule for when the degrees are equal, the rule is, excuse me, that you take the ratio of the leading coefficients. It means you take the front numbers and you divide them. So that is our rule here. We say it is the ratio of leading coefficients. That one's a little bit harder to observe than the other two, but nonetheless true. Okay, so some major takeaways from this horizontal asymptote business. First of all, why are these rules true? And what exactly is a horizontal asymptote? Because can you cross it? I mean, we saw that example 4, I think we did. Does that happen in example 6? Let's see here. 3x cubed minus x and 2x squared plus x, or 2x. Let's see here. just want to see. 3x, oh my gosh. Hello. 3x cubed minus x. And, what was it, 4x to the fourth? I don't remember. Okay, yeah, that'll do. I don't know if this was, but if you notice, right, you see this curve here. It has x-intercepts at here and here, whatever 0.577 is, but it goes back down to 0. And so the idea of a horizontal asymptote is it describes the end behavior of the graph. It describes what is happening on the left and right side of the graph as x goes to infinity or negative infinity. It does not really have to do with, oh, do you touch it or not? Talking about where's the function going, yeah? So, a few things to put down here. Say number one, a horizontal asymptote describes end behavior. Describes, oh my gosh, I can't write. I really don't like writing. Describes end behavior. That is, as x goes to positive infinity, f of x approaches the horizontal asymptote. That's what it does, right? As I go to the right forever, then the function approaches the horizontal asymptote. But this is true for both sides. If you go to the negative infinity, it also approaches the horizontal asymptote. That's what they have in common. So that's what it's doing, right? That's what it's about. Number two, you can, so I'm gonna, you know, let's capitalize all of those. You can touch or cross a horizontal asymptote. Yeah. If you have this conception that you can't ever touch them, that's not true. Okay, not true at all. And we saw that. And there it is. There's the rules for horizontal asymptotes. So make sure you know those three things, okay? You'll have to, you have to memorize it, but yeah. Real quickly, I do want to talk about why, because you found these rules by observation, but a deeper conversation is, well, why? Why is it 0 if it's more on if the degree on the bottom is bigger? Well, maybe I'll do this in blue. Consider x squared plus blah, 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 blah. On the denominator, consider x cubed. No, sorry, I wanted to do the other way around. X squared plus blah, 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 blah over x cubed plus blah, 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 blah. Yeah? So the highest degree term is sort of the dominant, like it dominates the polynomial because it's going to always be bigger, right? So, for instance, if I say x squared plus like yada, 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 if I make x 1,000, well, if it's just like 2x minus 1, 1,000 squared is huge, but 2 times 1,000 compared to 1,000 squared, right? And then minus 1? I mean, who really cares about that, right? 1,000 squared is way more important. Has way more to say about the numbers. And the same is going to be true on the bottom. The cubic is going to be more powerful than anything out here. So I'm really only concerned about the highest power because it's sort of dominating what's going on in the top or bottom. But then I compare 1,000 cubed to 1,000 squared. You see, 1,000 squared is really big, but 1,000 cubed is 1,000 times bigger than 1,000 squared. In fact, 1,000,000 squared compared to 1,000,000 cubed, 1,000,000 cubed is 1,000,000 times bigger than 1,000,000 squared. So the cubic far outpaces the square, right? You can see this growth. X squared is 1, 4, 9, 16, 25. Those are my perfect squares. My perfect cubes are 1, 8, 27, 64, 125. The growth rate of cubic far exceeds the growth rate of quadratic, right? This idea of growth rate with respect to degree is often referred to the order of a polynomial. If you take discrete math, this is going to be an interesting sort of topic to talk about. By the way, discrete, it's a math class in college. A lot of computer science majors have to take discrete. But you talk about the order of polynomials and this kind of how they dominate stuff. But it doesn't have to just do with polynomials and other things too. Anyway, if the bigger number is on bottom, well, if this is 1,000 times bigger on bottom, then that's going to be really, really close to 0, right? And so that's the idea that as x grows larger and larger and larger, you're going to become smaller and smaller and smaller because you're dividing by a bigger and bigger and bigger number, right? So y is 0. That's why we have that rule there. Same idea for the other ones, if you kind of keep this idea of growth rate. If you have a larger growth rate on top compared to bottom, then, well, the top sort of outpaces the bottom, right? This grows faster than the bottom is going to. So it's going to grow, 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 which means it's not shrinking down to 0 and it's not staying level, it's growing. So as x goes to infinity, f of x is going to grow to positive infinity, or maybe negative infinity. Maybe it goes all the way down to that. But the idea is its magnitude increases because the numerator outpaces whatever is going, the growth in the denominator, right? And so, because of that growth, not that, please. Because of that growth, I don't have a horizontal asymptote. Yeah, it's always growing. It's not staying constant or flatlining anywhere. Sorry, I got the sniffles. Anyway, the last one is the ratio of leading coefficients. If I say, well, if I had x squared over x squared, these grow at sort of the same rate. They sort of nullify each other, or they since they grow at the same rates, then they're at the same pace, right? But if I have 3 times x squared and I have 2 times x squared on bottom, well, you could kind of think of these as canceling because their growth rates are very similar, right? I say similar because, it could be x squared plus 2x minus 1, and then this one could be plus 5x plus 2, so maybe the bottom's faster. But relatively, as you grow to infinity, it's the highest one that really determines that behavior. And if you think of that as crossing out, all you're left with is 3/2. So it levels out at 3 over 2. That's why you take the ratio of leading coefficients when the degrees are the same. Hopefully that kind of illustrates why we have these rules. But yeah, that's it. Okay. Sorry, excuse the sniffles, okay? It's just allergies. Thankfully, I'm not sick. The wedding is Saturday. I sure hope to not be sick. Okay. Removable discontinuities / holes. This is my favorite part of the lesson, by the way. I love this part. So it says, using a graphing application, graph the following. Okay. So I'll do it. It's fine. This video is already going to be long. I'm just going to go ahead and do it, okay? I got x minus 6 over x plus 2. Sure. Let's do it. X minus 6 over x plus 2. Ta-da! There's my graph. Fantastic. Let's go graph the other one. X squared minus 8x plus 12 over x squared minus 4. Okay. X squared minus 8x plus 12 over x squared minus 4. Oop. Minus 4. Oh, well, look at that. The blue is the red. The blue and the red are the same. Oh, that's interesting. So it seems their graphs are the same. Do they have the same asymptotes? I mean, it sure seems like it, right? The blue one seems to have an asymptote at 1, I think. It says y equals 1. And that makes sense based off those rules. Sorry, I said 4. I meant 1. No, 1. There we go. Yeah, it's leveling out at 1. Yeah. Okay, that makes sense. And then it has a vertical asymptote at -2. Yeah, that's true for both the red and the blue, right? So they both have vertical asymptotes at x equals -2, based off my image of the graph. This one's x equals -2. And the horizontal asymptote was 1 for both of them. Fantastic. Now, what's f of 2 and what's g of 2? Well, f of 2 is, let's see, x minus 6 over x plus 2. That's 2 minus 6 over 2 plus 2. That's -4 over 4 is -1. So f of 2 is -1. Good. Good. What is g of 2? Well, they seem to be the same graph, so pretty sure g of 2 is -1 as well. But I mean, let's just play along with Mr. Spake. Maybe he has something to say here. 2 squared minus 8 times 2 plus 12 over 2 squared minus 4. Okay, let's calculate that. 2 squared, that's 4 minus, that's going to be 16 plus 12 over 4 minus 4. Well, 4 minus 16 is -12 plus 12 is 0, and 4 minus 4 is 0. What? Well, that's not -1. 0 divided by 0, that's indeterminate. You say, what? I don't know 0 divided by 0. I can't determine that. I say that's indeterminate. I'm going to say indeterminate. By the way, you say, Mr. Spake, isn't it called undefined? Well, you could, but more specifically, 0 divided by 0, it's a little bit more special than like 1 divided by 0. 1 divided by 0 we call undefined. 0 divided by 0 is very special because there's a lot of different things that can happen if you allow that. And infinite possibilities of, how do you call them? Oh my gosh. Things that are in conflict with one another, like counterexamples. I can't think of the word for some reason. Not quite paradox, but whatever. Contradictions, that's it. If you allow 0 divided by 0, you get a lot of different contradictions because you get all these infinite things. So it's indeterminate. We don't know what it is. But whatever 0 divided by 0 is, it ain't -1. So does f of 2 equal g of 2? No, it does not. They're actually not the same thing. So even though they have the exact same asymptotes, they look like the exact same function, at a single point 2, for x is 2, they're not the same value. Now, I'm going to factor g of x. It's x squared minus 8x. So that's going to be x minus 6 and x minus 2. We'll factor that numerator of this guy. And x plus 2, x minus 2 is the difference of squares for the denominator. And now you'll notice that this is similar or related to f of x because f of x is x minus 6 over x plus 2. Notice if I crossed out the x minus 2's, I mean, they're dividing each other, right? X minus 2 over x minus 2. Anything divided by itself is 1. So if I just divide that out and make it a 1, then I have f of x. So they're the same function. But they're not. I mean, first of all, by looking at the denominator, I had this rule, right, from earlier, way over here. Look, the factored form of this one was x plus 2, x minus 2. I had 2 vertical asymptotes, but on this one, well, 2 is not defined. It's undefined. It's indeterminate. And I only have a vertical asymptote at -2. So what's happening? Wait, hold on. What's happening here? You might be wondering. You say, Mr. Spake, will you just shut up and tell me? I said, yes, I'll get to it. But it's curious, right? Is x equals to a vertical asymptote? No. Based off our rules earlier, based off factored form, it would suggest that it is. It's undefined for 2, but it's not a vertical asymptote of g of x, right? It's something else. And that something else we call a removable discontinuity, which you can also call a hole in the graph. And by the way, discontinuity or continuity is going to be a pretty major topic of calculus. You're going to be very interested in continuous functions and where they are not continuous, okay? And what I tell you now is a good baseline introduction, but your true, genuine understanding of this is really going to build throughout pre-cal, throughout calculus, okay? So what you have is a hole at 2, and I'm hoping Desmos will cooperate with me here. Will it if I... Okay, you can kind of see. I just actually... Notice right there, at 2, it says it's undefined, right? When x is 2, you don't have a value, and you might even see, that open circle that's there, right? So it's an open circle on 2. So it's literally a point that's missing from the graph. Question is, what is that point? Well, I mean, you could zoom in here. Looks like it's at 2, -1, right? Yeah, that sure seems like it. Let me look at the y values. They're going up, 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 approaching -1, and then it hits undefined, but then it just keeps on going like it's normal, right? In fact, if I look at the similar functions, so this is f, right? Not g, but f, and I look at 2, it is defined, there it is, at -1, right? 2, -1. So there is a hole in the graph of g, right? The hole is at 2, -1. That is the point that is missing. And that point that's missing we call a discontinuity, a removable discontinuity, because it's like it was there, but you could just remove it, right? It's just like this point that if you take that out, the rest of the graph behaves the same. Nothing fishy is happening around it like an asymptote, right? It's not like, going and stretching to infinities. It's just not there, right? So, when do we do holes versus asymptotes? Well, you might notice that what caused the hole was this 0 over 0 business. Because I had x minus 2 on top and bottom, this created a hole in the graph. So, I'm going to work an example here. And we're going to put all these sort of pieces together. So f of x is yada, yada, yada. First thing I'm going to do is start by factoring. So, on the top, 3x squared minus 3x. The GCF here is 3x, and I get x minus 1 left behind. On bottom, it should be x minus 2, or x plus 2 times x minus 1. So what's happening here is you've got x minus 1 on top and bottom. Just like the example we did, that's going to create a hole in the graph. Now, how do I find that hole? Well, this function is equal to 3x over x plus 2, provided x is not 1. And so I want you to think about that, right? Kind of like how we said it's similar to f of x, right? Like up here. We said, hey, g of x is this thing, f of x is this thing, and g of x has f in it, right? I mean, in this match, all that's really different is it has this common factor on top and bottom added to it, which creates a hole, right? But this function and this function, they're basically the same image. The only thing is they differ at 2. So what I'm doing here is I'm saying, hey, this function, or rather, the original one I start with, you can kind of simplify it as 3x over x plus 2, but you have to specify this is true only when x is not 1. If x is 1, then it's not defined, right? So I have a hole. I'm going to put this in blue. You have a hole at x equals 1. I say this right here causes a hole. Now, how do you find the hole, right? To find the hole, plug in 1 to that function. So say find hole. You say 3x over x plus 2 when x is 1. So what we get here is 3 times 1 over 1 plus 2. That's 3 over 3 is 1. So that's the y value, okay? So a hole is a point. It's a point that's missing from the graph. It's a discontinuous gap, right? Not so much a gap, but a hole, a point, right? So I call it a hole. It's happening at 1 because x is 1. And on the other function that looks just like it, at 1, it's 1. I hope that's not confusing. You plug in 1, you get out 1. But the point is, that's the point that's missing from this graph. Because if I put in 1 here, well, I get 1 minus 1, 1 minus 1, I get that undefined thing. So 1 comma 1 is a hole which we are going to draw as an open circle. Make that a little bit tinier. There it is. So don't make it a point that's filled in, but rather an open circle to represent a hole. Vertical asymptote. Well, because x minus 1 is a hole, we can just kind of ignore that. The vertical asymptote, if you remember our rules that we talked about earlier, is the roots of q of x. Although we're watching out for holes now because that's a new idea. So what makes the bottom 0? What makes x plus 2 equal to 0? Well, you subtract 2 from both sides, you get x is negative 2. So that's my vertical asymptote. X is negative 2. So I will make a vertical asymptote here. All right. Now for horizontal asymptote. So I look at the degrees, right? I remember these rules that I had right here. So I look at the degree, if they're less than, the same, or greater than. In this case, they are the same because it's 2 squared, right? So it's squared on both top and bottom. And if the degrees are the same, then I take the ratio of lead coefficients. I do 3 over 1. So y equals 3 over 1. That's just 3. So I come over here, and I draw this. Nice. Okay, so how do I draw this graph, right? Now, maybe you know what this graph looks like, maybe you don't. You do have a hole down here, so you're probably thinking, the graph just does that, right? And you know what? That's a pretty good guess. But you know how we saw earlier that you can pass horizontal asymptotes? I mean, we saw that, right? A horizontal asymptote isn't a boundary. It's not something you can't touch or go through. So who's to say this graph doesn't come down from above, go through this hole, and then approach the asymptote? I mean, who's to say? How do you know? How do you know that it's doing this, really, right? Because if you thought it was the horizontal asymptote, I told you that it's not, right? How do you know it doesn't look like this image, which it very well could? Well, you need to know which direction it's coming from at the asymptote. And so the way you do that is we look around the asymptote to see what its behavior looks like. So I notice an asymptote here at -2, right? So what I'm going to do is I'm going to look at the behavior. I say, look at the behavior around the asymptote. Earlier in this video, I said you can only either approach up or approach down. That's it when you deal with vertical asymptotes. It can only go up or it can only go down. Which means if this gets closer and closer and closer to a vertical, If I pick something really close, like right here, it's either going to be going up here or it's going to be going down here. And if it's reaching towards positive or negative infinity, if you know that the value, if you know that close to that asymptote it's positive, very well likely it's going up. If you know it's negative, very well likely it's going down. So what I'm going to do is I'm going to sort of look at, let's say, x is negative 2.1. So you see negative 2.1 is like right about there, maybe even less, right? It's just to the left of the asymptote. Is that value positive or negative? Because if it's positive, then I'm probably going to have a point up here somewhere. But if it's negative, I'm probably going to have a point down here somewhere. And knowing whether it's positive or negative tells me whether the curve goes up or down on that side of the asymptote. So look at your factored form. Yeah, look at factored form and plug in that point I chose, negative 2.1. 3 times a negative 2.1 is a negative value. Negative 2.1 minus 1 is also negative. Negative 2.1 plus 2, that's negative. And negative 2.1 minus 1 is also negative. So I have a negative, a negative, a negative, and a negative. That is 4 negatives, right? It's negative, negative, over negative, negative. 4 negatives make a positive. So what that means is, on the left side of negative 2, all right, here, it's positive, meaning it must be approaching upwards, must be reaching upwards this way. And it's going to bend towards the horizontal asymptote because that's where the behavior ends. So it's going to, we're just going to bend it towards the horizontal asymptote. So that is that curve. I didn't quite like that. There we go. A little bit smoother. I like it. Okay? So I'm testing around the asymptote, but you must test the right and left side. So I'm going to test to the right side of negative 2, about negative 1.9, and I'll see that negative 1.9 times 3 is negative. Negative 1.9 minus 1 is negative. Negative 1.9 plus 2 is positive. Negative 1.9 minus 1 is negative. So I have 3 negatives and a positive. 3 negatives and a positive. That yields a net negative. So on the right side, it is coming from beneath up. So it's going to kind of come up, curve towards this hole, right? And then continue forth. And that is the shape of the graph. Nice. So that's your image, yeah? For domain and range, you'll notice that more than one thing makes this function undefined, right? A vertical asymptote, if I plug in negative 2, that makes the denominator 0, undefined. But also the whole. At 1, 1 comma 1 doesn't exist on this graph. 1 is missing from the domain. So your domain is all real numbers, but it's from negative infinity up to negative 2, and then it continues from negative 2, but it stops at 1, right? It doesn't actually include 1. And I'm talking about that one, right? Then it continues from 1 to infinity. You can kind of see that in our graph here. Man, this video is long. It's okay. I'm just getting tired. I'm sure you are too if you've been watching this whole thing. God bless you. You're going, here we go, at negative 2, right? So you're getting close to negative 2, but you're not touching it. And then you're going from negative 2, la, 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 but then there's a hole here at 1, and then you continue. So see what's happening is negative infinity all the way to -2, continue all the way to 1, and continue on. That's why it's negative infinity to -2, union with -2 to 1, union with 1 to infinity. That's why. If you can repeat this for the range, it's all the way, it's from negative infinity up, up to 1 right here. Continue to 3, and then continue on past that. So it's missing 1 and 3, right? So my range is negative infinity up to 1, union 1 to 3, union 3 to infinity. Nice. And that's a graph. Whew. That's a lot, right, guys? That's a lot. This is a great lesson, though. So you've got all the rules, right? You've got vertical asymptotes, you've got horizontal asymptotes. Now you've got holes, and now you can get started. Now the actual fun begins. Let's graph these things like we just did. But what happens if they're really complicated looking, right? This one still looks like a parent function, right? This is just your typical rational. Let's find some fun ones. So, example 1. And by the way, here's all the rules, right? So everything you need to know is right there. Holes happen when you got a common factor on top and bottom. You can find the vertical asymptotes, we'll find the zeros of the denominator, and then the rules for the horizontal have to do with the degree right there. So, example 1. Let's factor this. I'm just going to leave the top as 1 minus x. I could factor out a negative, but that's okay. On the bottom, it's going to factor as x minus 3 and x plus 2. Or, sorry, x plus 1, sorry. So, do I have any holes here, like I was saying earlier? Well, no. Holes happen when you have like x plus 3 over x plus 3. If you see that, then there's a hole. The numerator and denominator share no common factors, so there are no holes, none. So what are the vertical asymptotes? Well, the vertical asymptotes are what make the bottom 0. 3 minus 3 is 0. Negative 1 plus 1 is 0. So the vertical asymptotes, well, I have 2 are 3 and negative 1. So I can graph those. Here's 3. Here's negative 1. Horizontal asymptote, I look at the degree. So the degree on top is 1 and on bottom is 2. So that's 1 to 2. Bottom is bigger. So this rule, when the degree of the top is smaller than the bottom, it's y equals 0, right? So my horizontal is y equals 0. So I've got a dashed line here, like so. Okay. X-intercept. So to find an x-intercept, you set the function equal to 0, right? So x-intercept, we set 1 minus x over x minus 3 times x plus 1 equal to 0. But the thing is, you can multiply this thing by x minus 3, x plus 1 here, and that cancels out here. But then if you multiply it to the right side, 0 times that value is just 0. So I get 1 minus x is 0, meaning 1 is x. So I have an x-intercept of 1, 0. By the way, before I proceed, I want to talk about that you can shortcut this. To shortcut getting the x-intercept, solve p of x equal to 0. Yeah, meaning set the numerator equal to 0. This is actually how you can find x-intercepts very quickly in factored form by just setting the top to 0. And the reason is, whatever this denominator is, whether it's simple or ugly or complicated, no matter what it is, when you set the entire function equal to 0, every time you're going to multiply by the denominator on both sides to get rid of the denominator so you can find x. But 0 times anything is going to be 0. So there's no point in doing that every time. Just look at the top. When is the top 0? 0 and x is 1. Okay. To find the y-intercept, you set x equal to 0, right? So the I'll stay in red. The y-intercept is you set x equal to 0. So it's 1 minus x over x squared minus 2x plus 3. Minus 3, okay? Thing is, if you just make x 0, 1 minus 0, 0 squared minus 2 times 0 minus 3, you just get 1 over negative 3. So my y-intercept is 0, negative 1/3. So to shortcut this, just forget the x's, cross them out. Gone, that's 0, that's 0, that's all 0. What am I left with? 1 over negative 3. That's it. It's negative 1/3. Okay. So let's put those points down. I got 1 comma 0 here. And then, you know what? I'm going to do blue. So I've got 1 comma 0 here, and I've got 0 comma negative thirds right there. All right. Now, what does this curve look like? So I have to figure out if it's going up or down, up or down, up or down, up or down. So you would need to test the left and right sides of both asymptotes. So my first asymptote is negative 1. Let's test negative 1.1. That's to the left of negative 1. Look at factored form. 1 minus negative is going to be positive. Negative 1 minus 3 is negative. So I got so what I've got here is positive over negative, and then negative 1.1 minus 1 is negative. This gets me a positive. So on the left side of 1, negative 1, it's going to be going up. So it's going to come from up, and on the left side, approach that horizontal asymptote down at 0. Okay? Now I do the other side. X is negative 0.9. So do 1 minus negative 0.9, that's going to be positive. Negative 0.9 minus 3 is negative. Negative 0.9 minus plus 1 is positive. That's 1 negative and 2 positives makes a negative. Means it's going to... Oh, I wanted to do this in blue, sorry. Let's make the curve in blue. There's a lot of red on the screen, right? So it's going to come on down to the asymptote like this. Okay. On the right side, it's negative, so it's going to be coming from below. It's going to come up, and it's going to come through these points like this. Question is it going to continue up, or is it going to bounce back down? So that's why I keep testing. I must test to the left of 3 now. Let's try 2.9. 1 minus 2.9 is negative. 2.9 minus 3 is negative. 2.9 plus 1 is positive. All put together is positive. So on the left side of 3, it's positive. It's going up. So this is going to bend towards up there to positive infinity. Nice. Oh, I love this. And then lastly, I just test one more. I'm almost done. I test, let's say 3.1. 1 minus 3.1, is negative. 3.1 minus 3 is positive. 3.1 plus 1 is positive, so that's a net negative. So it's going to come down from below and reach upwards towards the horizontal asymptote. And that's my graph. Yeah? That's what the image looks like. And by the way, we can graph this in Desmos. 1 minus x over x squared minus 2x minus 3. Let's type, oop. I'm almost done, guys. It's great. I mean, you can click off, but I have to actually keep going. X squared minus x minus 3. Hey, there it is. We did it, right? It had a horizontal asymptote at 0, had two vertical asymptotes, one at -1 and one at 3, right? X equals 3. Oh, did I mess up a sign? Was it plus? Yeah, was it plus? Wait, what was it? Oh, 2x. That's why. Minus 2x. There it is. So there's the 3. And then x was -1 over there. Yep. That's the graph I drew. Awesome. So my domain, you'll notice, I don't touch the vertical asymptote. So it's -infinity up to -1, continues from -1 to 3, then continues beyond 3 to infinity. Your range, however, is all real numbers. The reason why being, look at this middle curve. It goes all the way down to -infinity, comes up, and is defined for all real numbers, up and down. That curve tells you it's all real numbers. And you can notice, even though this branch don't seem to touch that horizontal asymptote at 0, this one does because it crosses through at 0. And we found that x-intercept right there. Awesome. Awesome. Okay. By now, if you get the gist, you get the gist. And so you don't need to see another example. But I'm going to do one more example for the sake of the video and then end it here and then go enjoy my night and film 7.3. Which I will do. But, I'm going to get dinner first probably. Where should I get dinner? I don't know. I was low-key thinking Raising Cane's. I don't know. My one of my friends, Jacob, he's coming to my wedding this weekend on Saturday. His girlfriend works at Raising Cane's, and he's bringing me a hat. So I'm going to get a Raising Cane's hat. Employee exclusive. Hopefully they don't find her. If you work for Raising Cane's and are watching this video, don't tell anybody that is what we're doing. Okay. Let's do this problem. Say, Mr. Spake, shush. Let's factor this thing. So I got 5 times x plus 2. On bottom, I got x minus 5 and x minus 2. That's factored. I mean, you got to factor, right? Do I have any holes? No. I don't have any holes. Not in me. I'm a complete person. There's no thing matching on top and bottom, right? X plus 2 and x minus 2 are not the same thing. So there are no holes. Vertical asymptotes make the denominator 0. So x is going to be positive 5 and positive 2. So we got a 2 here. Guys, am I doing all right? Is this correct? 5 into, I mean, yeah, seems good to me. Okay, all right. I'm just making sure, I factored that correctly. Horizontal asymptote, well, the degree on bottom is bigger, so it is, again, 0. It's not always going to be 0, but in this example, just like the last one, it is. The x-intercept is going to be at -2, 0, and I can see that because of the numerator. -2 plus 2 is 0, so that makes the top 0. So that's an x-intercept. We'll make this in blue, -2, 0. Y-intercept, Well, you could just look at, so cancel the x's. You're just making the x's zeros, right? So you got 10 over 10, that's 1. So 0, 1, right here. I don't know why. I just don't know if I like this. It's going to be fine. It's okay. And now let us find the rest of the shape of this graph. So, where's it going? So I got to test, right? We're going to test to the left of 2. Let's test 1.9, factored form. I'm looking up here, by the way. That's where my eyes are. Putting in 1.9 for all my x's and looking at the sign. So 5 times 1.9 plus 2, that's going to be positive. Let's just say that positive over 1.9 minus 5 is negative. 1.9 minus 2 is negative. So this is going to be a net positive. So it's going to be coming from above like this. So it's going to come on down. It's going to come through both these points. Now notice something. It's going through both these points, and it's crossing the horizontal. So it's sort of gonna dip beneath, but then it has to bend back. Yeah? The idea is you must approach the horizontal asymptote. It describes the function's end behavior. So it's crossing it, but it has to bend back and go towards that line. It's not going to go down forever. Yeah? So please, don't make a curve that does that. That's not true. It has to follow the horizontal asymptote. That's the end behavior. Let's see what's going on elsewhere. Let's look to the right of 2, so 2.1. 2.1 plus 2 is positive. Well, you can pause the video, do this yourself. 2.1 minus 5 is negative. 2.1 minus 2 is positive, so I get negative here. Means on the right side of 2, it's going to come from beneath. Now, I can kind of logic my way through this. I don't have an x-intercept here, so in order for this to go up, I would need to touch the x-axis, which I don't. So it's going to bend back down, okay? But if you don't trust me, then that's fine. It's okay. You can. I don't take offense. To the right of 5, to the left of 5 is 4.9. So 4.9 plus 2, that's going to be positive. And then 4.9 minus 5 is negative, and then positive. Hey, what do you know? It's negative. So it's going to come up somewhere and then come back down. And it's going to be negative down there. Okay? And then x is going to be 5.1. We're going to plug that in. 5.1 plus 2 is positive. 5.1 minus 5 is positive. 5.1 minus 2 is positive. Gets me positive. So on the right side of 5, it's going to be up from positive infinity, extend downwards. Doesn't look like we're going to cross this horizontal asymptote. We're just going to get next to it because I don't have any intercepts there. And that is the shape of the graph, right? Now you notice I have a blank for domain, which you can fill out because it's not the vertical asymptotes, right? It's from negative infinity up to 2, continues between 2 and 5, and then, oops, and then, oh my gosh, can't write, and then it continues from 5 to infinity, right? So, that's my domain. But you notice, I said, you can't find the range. You mean, what do you mean I can't find the range? Well, of this great image you've drawn, where's that point? I mean, that has a maximum, right? A local maximum. It comes up and it peaks somewhere, but who's to say I don't draw it that way? Who's to say I don't draw it this way, right? I don't know where the peak of this is. Moreover, I don't know what the lowest point of this is. I mean, yeah, I know that it crosses here, but it comes down, it's going to hit a lowest point, and then it's going to go back. I don't know what those points are. And if I graph this function, 5x plus 10, right? 5x plus 10 over x squared minus 7x minus 10. Yeah, that looks like the graph I drew, right? I don't have quite the same curvature in the middle here. Wait, was it 7x? Did I do something wrong, guys? Negative, plus 10. Silly me, silly. It was plus 10. There it is. Yeah. So this graph, sorry. Kind of the same image though, right? You can see that I cross here at -2, and Desmos is telling me there's a lowest point at -0.232. And it's telling me this highest point is at a -11.991. So there's this huge gap in the graph missing for the range. I don't know how to find that. Except I do, because I've taken calculus. I know that I can take the derivative and find the local max and mins, and then I know the range of the function. But you haven't taken calculus yet, right? You're just in Algebra 2. Unless, of course, you're a calculus student revisiting this video, in which case, hey, why don't you go find the range? Go use the quotient rule and take the derivative of this thing, and you tell me what the range is. That's fine. I'm not going to ask our Algebra 2 students to do that. Do not worry. Range is not a major focus of this test, okay? Or of this unit even. You can't always find it, okay? I might ask you now and then, if it looks visible, you can really just look at it and tell, okay, it's easy enough, tell me the range. But if it's something like this, you don't know how, it's fine, okay? You don't get a calculator, it's okay. And that is that. Oh my gosh, this was a great video. I mean, it was really long, and we had, we had some sniffles like that. But, I'm going to go blow my nose, and I'm going to go get some food, and I'm going to have a good night. I'm going to come back and probably charge the iPad while I eat and start 7.3. You say, Mr. Spake, why are you telling me this? I don't know. I'm going now. Have a great night. Thanks for watching this video, and I'll see you in the next one.